Thank you. Okay. Anyway, here we are again. We will talk now about fields in physics. Most of the interactions, of course, we explain in fields, no, by using fields. But what is a field? Initially, in the times of Newton, Newton used it as an artifact, as a way to represent the gravitational interaction. Remember that if you want to represent the interaction between an apple and the earth, you have to put some arrows. He imagined there is a field. Well, he didn't know. Actually, Newton was never happy with his theory. And I will tell you why. Because this instantaneous interaction between the moon and Earth, who can you explain it? Or who can you explain that, I put this remote control here. This is a remote control. You can see it. If I don't touch it, I let it fall, naturally it will collide with the floor. Instantaneous interaction, are you sure? Newton was really unhappy about that. And this was solved also by Einstein, because of course the gravitational interaction propagates at the speed of light. And this is what the Einstein equation says. But do you know that you apply weak field approximation? You take the Einstein equations, weak field approximation. I have done that thousands of times. And then you obtain, it's like a perturbation, and that perturbation propagates at the speed of light. It's gravitational waves. So this is an example of field. Represent the fields with arrows. When you do a laboratory of physics and the professor asks you, represent this experiment, normally use the arrows. The longer the arrow, the higher the intensity of the field, etc. I think I don't have to mention so much about gravity because we see that everywhere. We have gravitational field, we have electric field. The electric field also has lines. This is a negative charge. For negative charges, evidently the convention, because this is purely conventional. I mean, you have to fix a convention. Every time you do physics, you have to fix some convention. And then one convention is this marker doesn't work. Let me use the other marker. These markers, they can work like that. Marker. The convention is that the electric field reach the negative charges. So the negative charge is a sink of electric field lines. I explained that before. You put a positive charge here, the electric field goes from positive to negative charges. Now, what happens is there is no charge where if you have a positive charge, the electric field goes to the infinity. Technically, because anyway, remember the electromagnetic interaction is infinite range interaction because it's propagated by photons, and photons are massless. Whenever the propagator of the interaction, or the particle which propagates interaction, is massless, which is the case of gravity and electromagnetism, the interaction is infinite. Then, once again, I repeat, why gravity dominates a large scale? Because there is no negative mass. Let's say macroscopically, the air is neutral. If you go to the space with a telescope, whatever, you will see equal positive and equal negative charges. And the natural tendency of any object is to become neutral. You charge this object and you stop charging, you stop applying the voltage, and it will become neutral. It will find the way, the configuration will arrange, it will start to spread charges everywhere until it becomes neutral. All the objects in the universe have the tendency to become neutral, macroscopically neutral. That doesn't happen with gravity. Gravity is cumulative, has only one positive charge, which is the mass. The mass is the charge of gravity. And when you go larger, it accumulates. So in the larger scales, you don't see electromagnetism because it cancels positive and negative charge. You see only gravity. That's why gravity dominates. Even being the weakest force, gravity is the weakest force. Incredible, because we feel it every day, no? It's incredible that it's the weakest force. For me, it was shocking. Oh, can be the weakest force when I studied these things for the first time. It's impossible. Well, yeah, it's the weakest. Even the weak interaction is stronger than gravity. The weak interaction, which happens in the decays of some materials, no? Also, in nuclear reactions and so on. We have the magnetic field. well, the air, we were talking about that during the break, no? The magnetic field of the air, that Mars doesn't have this magnetic field. The motion of charges internally generates a magnetic field of the air. The way of represent, there's a north and south pole, naturally, which not necessarily coincides with our north and south pole. Sometimes it's a little bit shifted, no? But anyway, there are some magnetic lines which actually protect us from some external threats, no? As you perfectly see in the news. No? And what's the reason when a charge moves through a magnetic field experiences a force? You will see that later when we study magnetic forces. But keep in mind something about magnetic force, difference between magnetic force and electric force. Electric force may work because it points in the direction of motion of the particle. The magnetic forces points perpendicular to the particle. They don't do any work. They don't work. They are lazy. They point in perpendicular. You can learn, magnetic is lazy. This is the way to remember. But you will understand that conceptually when we go to that point. So now electric and magnetic fields were, as you know, they are manifestations of the same phenomenon. We will see later. But for the moment, let's review a little bit. Again, we have positive and negative charge here. The electric field goes from the positive to the negative charge. There is no magnetic field here because these charges are not moving. Magnetic fields are generated if they start to move. If these charges start to move, immediately there is a magnetic field appearing, and that magnetic field will rotate around the direction of motion of the charge. All the magnetic field lines are closed. They don't diverge like the electric field lines. Electric field lines go from one source and they expand, but magnetic field lines always remain in a circle, from one pole to the other, etc. Now, when you have many charges, you have to apply the superposition principle. For example, if I want, this is an exercise every engineering student has to do. They put many charges, distances. It's a geometric problem. It comes out to be a geometric problem. Then they ask you, what is the force this charge feels? And then you have to play in this way. You have to analyze what is the effect of each charge over this charge. Then, for example, this is a negative charge, it will attract. Then there is a force in this direction, in that direction. This charge will repel, so it makes a force in this direction. And we put labels, 1, 2, 3, then this is F1, 2, F. I mean, it depends which labels you use. But I mean, you have to assume all the effects the same, this charge over this charge. It creates attraction with a force here. Let me use a different marker. A force in this direction. There will be a force in this direction. There will be a force in this direction. This negative charge will attract, so it will make a force in this direction. This one, positive, it will make a force in this direction. And this will make a force. You have to sum all the forces. And in the system is in equilibrium, of course, the sum of all these forces must be zero. In other words, if I put these arrows one behind the other, they have to close. They have to create a polygon. Closed. If they don't close, there is no equilibrium. It means this charge is accelerated. Is the graphical way to see a body is in equilibrium or not? You put the arrows one behind the other, they have to close. If they don't close, it means this charge is accelerating somewhere. And the charge accelerates and it starts to move, it generates a magnetic field. And if it accelerates, it creates an electromagnetic wave. But this is the superposition principle. It means you have to sum all the effects that this charge receives from all the other charges. And vice versa. You can do the same exercise for each charge and so on. This is an example of the electric field lines. Look that they go from positive to negative, always. Positive, negative, positive, negative. In other words, the positive charges are the source of the electric field. The negative charges, they are the sinks they receive. These are a flow of water. Imagine the water is the fountain of water. goes out from here, and then this is the sink of water. But imagine that that water is just electric field. That's it. This is how I imagine. Now, if I duplicate the velocity charge, double amount of arrows will appear here, and so on. And vice versa, if I duplicate the charge here, double amount of lines will be absorbed. What happens if there are not enough lines to be absorbed? If you duplicate the negative charge, the other lines come from the infinity, from somewhere, which you don't know. Well, we already saw the Coulomb law. We don't have to do this part. Let's take a look at this electric field animations. Look at this. The first one is a positive charge. Let's assume that this is 1 Coulomb, and this is minus 1 Coulomb. When both are positive, they repel each other. Well, you can see that both of them expel electric fields. No electric field line goes from here to here. So this is the symptom that they repel each other. Because later, of course, you will see that the force, for example, the force will be like this, is equal to the charge, this charge, times the electric field, which this guy emits. And the electric field, what is the equation of the electric field? Is KQ of this charge, K1, let's call this 1, this is 2, divided R squared. And U, this is Q2, let's call this Q2, and let's call this Q1. Then you can replicate the Coulomb law again. When you replace this here, is KQ1, Q2 divided R squared. This is the difference between gravitational field and gravitational force. Also is the same. Remember that gravity is defined with only the source mass. Okay, the same is here with the electric field. So this is the animation. More animations. The same with negative charges. Same story, but now you can see that all the lines go inside. They don't go out. So for example, if an exam, I put you these charges like this, and I ask you paint the electric field lines, what would you do? You paint from positive to negative, positive to negative, positive to negative, and so on. This is a quadrupole, 4 charges. This charge is 3 times. So all the lines emitted by this positive charge go to these 3 sinks, because to the 3 negative charges. Now, what happens if I isolate this system like that, and I am very far away? I will not see any electric field. You know why? Because all the lines coming here. So I will feel that there is no electric field here. There is no electric effect, nothing. This is what I was saying before. The air is more or less like that. It's microscopically neutral. Well, of course, if you go microscopically, you will find differences, polarization of charges, etc. This is another example. Well, this is more complicated, but still, I think it's not difficult to do as far as you know the rules. The rules is, of course, the tendency of the electric field lines is to move upward radially, but when they feel the presence of a sink, they deviate toward the sink. And this is a single charge, of course, radially. They spell radially. And they are repeating again the same thing. Excellent. There is an analogy between electricity and water flow. Look at this. Imagine you have a water tank with the volume, and this is a waterfall. When you open this is how they create the water supply systems in the past. No, in the past, when they established a town, they didn't have the technology. They didn't have a pump, nothing. But they have to locate the towns in places that were located below the level of the water of the ponds or the lake or whatever. And they just put some system connecting that and then the water. And all what you have to do is to control the opening and closing. This is this this has an interesting thermodynamic analysis, which we will see later. Well, this is not the moment of going there. But basically, the flow of water can be analogous to the flow of current. The difference in pressure is equivalent to the difference in voltage. And there is a resistance when the water flows due to the friction of the walls. It's something we cannot cover here, but there is something called the Newton law of water when there's laminar flow. The flow, for example, the velocity of the fluid on the walls is zero, but it's maximal in the center. And it has shown there is an equation telling you the force, the frictional force between the walls and the fluid. And that's called Newton law in laminar fluid. Well, normally the fluid is turbulent. Turbulent is a mass, and that doesn't have any analytic solution. Normally people do simulations, experiments. The engineering people do many experiments and simulations, but there is no way to portray it analytically. It's related, but not exactly, because of course this let's put it this way: when you analyze turbulent fluids, you have some numbers, dimensionless numbers. There's the Reynolds number and other kind of numbers for analyzing models. For example, you analyze how a ship behave in turbulent waters, then it's difficult to model this analytically holy water. Then you have to do many experiments, and it's mostly trial and error, let's say. But there is no analytical way to. And chaos theory, of course, is when, like the butterfly effect, the famous butterfly effect. Some people study those kind of theories, which are very useful, but they are connected, but not in a very direct way. No, of course, when you analyze, for example, I construct a ship. I want to construct a ship, for example. I made a model, very small, and I test the model in waters, in some turbulent waters. But that model has to be scaled. You need to know the difference in scale between this model and the real model. And the way to analyze, to compare, is doing dimensionless numbers, using dimensionless numbers, which will allow you to compare directly what will happen here or what can happen in the real life world. Then, also, this is more like a direct test of a system. What I am trying to say here is that if we go to this simple example, is that when I open this, normally the water doesn't flow that friendly. It's a chaotic motion. There are many losses by friction, so there is heat, not as hot as the electricity, but still. And there is no mathematical simple way to model this fluid. Yeah? Of course, we have this the Navier-Stokes equations and so on, but of course there is no simple analytical way. You have to do some approximations and so on. So what we will not cover is so much in this class, because chaos theory is a little very, very complicated subject. Actually, it requires some skills, and it's like trying to predict how tiny variations in the initial condition of a system affect something which is very distant away or so. Or sometimes even if you have a pendulum, for example, and the pendulum lost a phase of 1 microsecond, and it's a cumulative effect, how that it affect in the long term for this kind of issues. So coming back to this example, the current is similar to the current of water. Voltage, as you could see, is equivalent to the difference in pressure I want to write something. I think you know perfectly this law. Voltage equal current. Is that this? Difference of voltage equal current times resistance. There's a resistance. Well, there is an equivalent one in pressure. There's also resistance. And there is also some quantity, let's call it U dot, measuring the fluid, the water flow. Well, there are analogies. With thermodynamics, there is also an analogy. This is the equation. I was just writing it. Voltage, difference in voltage is proportional or equal to the current times the resistance. This is the Ohm's law. Ohm's law, more properly. You can solve for the current, voltage, more voltage is of course more potential. It flows more electricity. More resistance means more resistance to the current, so less electricity will flow, or more dissipation. High pressure, low pressure, flow, etc. I mean, everything is analog. I will not emphasize so much because later when we see Bernoulli, we will see Bernoulli and hydrostatic later in this class. So we will not spend so much time in this part. The power, this is very important. The power, when the electricity flow, the power in watts, units of watts, is the current, which is in amperes, times the voltage. So this explains why we have to increase the voltage for transmitting the electricity. Let's assume that the power is also represented by I square R. How do you get that? If you represent this voltage IR from the Ohm's law. So these two expressions are equivalent. But what happened when they produce electricity in the hydroelectrics or in the plants, and they are going to send to your house, they have to increase the voltage. For a given power, they increase the voltage for reducing the current. So when we say high voltage, low amperage, and that reduces the losses because this is the power loss. This is the power loss. So there is, if you decrease the electricity, the amount of current, you reduce the losses in power. And vice versa, when the electricity arrives home, they increase the current and decrease the voltage. In that case, you will lose a lot of power, but it's normal because, for example, you have to use the iron, you have to use the oven, you have to use the television. It's normal that the electricity will dissipate in such a case. And that's what we want. We want that dissipation. Use other markers because these markers, I don't know, they put the worst markers today. I don't know why. Capacitors is something we will see later. Capacitors are very useful in electronics. They are equivalent somehow to the strings. They store charges. They can store charge. Inductors. Well, I will not go into details because I think we will see this later. Pistons, the diodes, etc. But these are issues of electronics which we will see later. Now I want to jump here to the Gauss law because Gauss law helps us to calculate electric fields. The Gauss law is telling me that the flow of electric field, if I have a charge, let's assume I have a charge somewhere. If I imagine I should run that charge with some imaginary surface. So the flow, let's put it flow, which is the integral of the electric field times the area is equal to the charge enclosed divided epsilon zero. Epsilon zero is the permittivity of the space. It's a constant which is measured already in textbooks anywhere. And this is the enclosed charge. So it means the flow of electric field here is this charge divided epsilon zero. And how can I calculate the electric field with that? Well, I can use the symmetry of the problem. Let's explore the symmetry. Instead of putting an arbitrary surface, I can imagine I should run this with a sphere. Let's assume I should run this charge with a sphere like this. And then I do this integration. Then the integral becomes trivial because the radius is constant. The radius is constant. This is a dot product, but the electric field is radial, is point, and the area vector is radial also. So this comes out to be, let's write here, the electric field times 4 pi r squared is equal to the enclosed charge divided epsilon zero. This is the way to calculate this integral. E times the area. The area of the sphere is 4 pi r squared. In an exam, I will ask this question for sure, the Gauss law. Then you can solve the electric field. It's Q inside divided 4 pi epsilon zero r squared. And what is this? The Coulomb law. You found the Coulomb law. Because the Coulomb law, in the Coulomb law, K, constant K is 1 divided 4 pi epsilon zero. So you could derive the electric field by using the Gauss law. And we can calculate electric fields of other geometries. And I will show you immediately how it works. Now, what happened? The Gauss law is so powerful. Let's assume that I made a surface. Look at the case here, this case on the right-hand side. This surface is not closing the charge, not enclosing the charge. So it means all the electric field lines which enter also escape. So the Gauss law is telling me that the flow, the electric field is different from zero, but the flow is zero. So if I ask you in the exam, what is the flow of electric field through this surface, which is not enclosing the charge, you have to tell me zero, because the same lines which enter also go away. But in this case, no, because when you enclose this, only lines are escaping. No line is entering. So it's different. Now, what happens if the charge is negative? Somebody will ask. If the charge is negative, the opposite. You just invest the arrows. And there are many lines entering, but no line escaping in such a case. And still, we can calculate. Now, let's go to other geometries. We can go to other geometries. We already saw how to apply the Gauss law in the case of spherical symmetry. Now let's go to a cylinder. This cylinder, this is a cylinder. This is a wire. This lambda is charge per unit of length, linear density charge. Let's put it here. Lambda is charge divided by length. Let's assume that it's constant. The lambda is constant. It's a constant density, so it means that this charge is distributed uniformly through the wire. I can surround imaginarily this wire with a cylinder. This cylinder is imaginary. I imagine. I put the cylinder surrounded, and I want to calculate the electric field with Gauss law. I have to use the symmetry of the problem. Obviously, the electric field goes from positive and escape. It will escape radially. Perpendicular to the surface of the cylinder. Now let's calculate the flow of these lines, and you will see that it's different to the radial case. The flow, let's apply Gauss law, integral down electric field area is equal to the electric field What is the area of the cylinder? The area. If I want to calculate the area of the cylinder, what is it? The length of the base multiplied by the height, right? So what is the length of the base? Is 2 pi r, no? Multiplied by the length of the is equal to what? Total charge epsilon 0. Well, the total charge is lambda by multiply L. So these L's cancel, and at the end you obtain that the electric field is lambda divided 2 pi epsilon 0 r. So what's the difference between this case and the previous case? The geometry of the problem changes. This is a cylindrical geometry. The other was a spherical geometry, and look at the dependence of the electric field changes also. So it means this field decays with 1 over r. Well, the case which has spherical symmetric changes like what? 1 over r squared. Then if an exam, for example, I could ask you, what is the functional dependence between the electric field and the distance for spherical symmetry? You have to say 1 over r squared. Cylindrical symmetry, you have to say 1 over r, and so on. And you can deduce that via Gauss' law. It's very difficult to calculate this analytically. Is possible, of course, by using the Coulomb law. It's possible, but it's much more complicated. We use the Gauss' law in problems with high symmetry, high degree of symmetry. And this, of course, helps us to do the calculations in a more compact way. Very easy and very compact. You don't need to be a genius to use Gauss' law, actually. The calculations are trivial. There are other problems. Of course, next class I will explore, I will go deeper into problems, but there are problems, for example, we will explore problems of this type, where you have a central charge here. This space is vacuum, empty, and there is another spherically charged body, but with a hole here. So this is a hollow body, this is a nucleus, and this is empty here. And I can ask you to calculate the electric field in different regions. Calculate the electric field here between 0 to radius A, calculate the electric field between 0 to B, calculate the electric field between 0 to C, and calculate the electric field outside. Now I will ask you a question quickly to see how you are. Let's assume that the charge of this inside body is Q, and this outside body is minus Q. What is the electric field perceived here? If I am here outside, I am an observer here, observing here. What? 1 watt. The electric field has units. Electric field has units. For example, inside, of course, depending on the charge you surround, the electric field starts to increase. When you are here, it starts to decrease 1 over r squared. When it's here, you are compensating Q with minus Q. It becomes more and smaller until it's 0 here. Outside is 0. You don't see any electric field because all the lines of electric field going out here go to the negative charge. They have the same magnitude in charge, only opposite in sign. So all the lines of electric field going from the positive charge go to the negative charge. There is no way you can see the electric field outside this material. Different story if it's a duplicate. If I duplicate the charge here, let's assume if I duplicate this charge, in that sense, half of the lines go to this material and half of the line goes out. In that sense, I will perceive some finite electric field, not magnetic field, electric field. These kind of problems we will explore next class, because this class is only an introduction to the phenomena of electricity and magnetism. There are other ways, there are other symmetries to consider. For example, if we have parallel plates, for example, these parallel plates you see here, You can also apply the Gauss law for calculating. You have to introduce a cylinder, but that cylinder enters perpendicular to here with an arbitrary area. Then, for example, let's assume that this is a positive charge and this is a negative charge. All the lines of the electric field goes from positive to negative, perpendicular like this. This could be a capacitor, for example, easily a capacitor. Then if I apply Gauss law here, it's simply electric field times area is charge closed divided by epsilon 0. But the charge closed, let's assume that these plates have a density of charge per unit of area. Then let's call that sigma will be charge divided area. Then sigma multiply area is the charge. Then let's put the sigma area epsilon. This area and area cancel, so at the end the electric field is sigma divided epsilon 0. This is a classical result in parallel plates. The electric field between parallel plates is constant. It doesn't decay. It doesn't decay with the distance. You can see that different geometries display different dependence with the radial distance. A spherical geometry decays 1 over r squared. Cylindrical geometry decays 1 over r. And these parallel plates, this is an infinite plate. It's like it's introducing an infinite plate. Infinite, it doesn't mean infinite in reality. It means large enough. Large enough such that you can ignore the effects of the age of the material. That's infinite mathematically speaking. Because sometimes, I mean, some guys who do physics and do probability, because we have a discussion, a debate in the other class about independent events, and they did a mistake because people take the mathematics sometimes too literal. And the mathematics cannot be taken so literally when we are in real life problems. Mathematics is just an approximation. You have to use logic and you have to interpret it correctly. In this case, infinity is large enough, like the board. Imagine this board is large enough, at least, or this board here, I can put a cylinder in mine here and I put a parallel board here. For me, for ignoring the effects of the edge, I can have to work in the center. So the board has to be large enough so that I have an area, a surface where this behavior is more or less valid. And the electric field will be a constant in such a case. So this is the Gauss law. So in summary, Gauss law gives you the flow of electric field through a surface. Is equal to the charge which you enclose, that surface enclosed, divided by epsilon 0. And with that law, you can derive under some geometry, symmetric geometries, you can derive the electric field. That's very, very important. Now that we have done electricity, we can then jump. We can jump to magnetic fields. Then let's open here. Magnetic field, look at this magnet. Look at this magnet. North and South Pole. This is in a laboratory, you can do this experiment. This is a special dust material, and you put a magnet. This material will align in some way, just like Terminator 2, when you saw the movie. The interesting part of the magnets is that you believe that if I cut the magnet in the middle, I will obtain North Pole and South Pole separated like positive and negative charges. This doesn't happen. You will obtain two magnets with North and South Pole separately. So there is no way to obtain a single monopole. As we have said, monopoles, they are not. So look at this. This is another example. There are two magnets. The lines flow from North Pole to South Pole. And if you put two magnets close to each other, they will exchange lines also in this way. Something to remark is that the magnetic field magnetic force is special. And I will explain why. I mean, let's assume that there is a charge in the middle of electric and magnetic field. There's a magnetic field in between. Then I will say this without the projection actually. Later I let's put it in this way. If I put a charge, let's put the magnetic field lines here. Magnetic field B pointing in this direction. And I put a charge here. And this charge is not moving. What is the magnetic force of this charge over this charge? 0. Why? How do you find the magnetic force? Somebody knows? Magnetic charge, velocity, the cross product, magnetic field. It's a cross product more generally. This means that the magnetic force is perpendicular to the velocity of the particle and perpendicular to the magnetic field. But if the particle doesn't move, if it doesn't move, this is 0. There's no magnetic force. Now let's assume that I move this particle perpendicular to the, I will put some velocity to the particle, different from 0 in this direction. Can you guess what is the direction? Of course, we will not calculate the magnitude. Let's calculate the direction of this force, magnetic force, based on the right-hand side rule of the cross product. Do you know the right-hand side rule, cross product? QE cross the first vector cross the second. This finger gives you the direction of the field, or the force in this case. So you can guess. You enter with this. The finger was for pointing people. Then after the finger of bad words, like this. You can cross the finger for insulting people. Just like this. And then it's going to the board. So it means this particle, when you move like this, it will make a circle. It will rotate this way. It will rotate the way I showed just now to you. It will keep rotating. In this direction, doesn't feel any force. Of course, let's assume that I push the particle a little bit. Newton said that it will keep, if there is no any external force in that direction, it will keep that motion. No? So it will be an helicoidal motion. Well, what is the characteristic? I want to calculate the work of this magnetic force. What's the work? I said that a moment ago. No? Magnetic forces are lazy. 0. They don't work. Why? Because they are perpendicular to the direction of motion. Remember when we study work, what is work? It's the dot product of the force times the distance. But dot product means the norm of the force times the norm of the distance cosine of the angle between the force and distance. The direction of the displacement, let's say. And of course, in this case, evidently 0. They are perpendicular. Cosine of 90 is 0. Then, of course, this force doesn't do any work. Different case. Now, let's assume that I combine this and I put an electric field together with the magnetic field, and I put the electric field in this direction also. What will be the motion of that particle? In which direction we move? Now I put an electric field parallel to the magnetic field, both of them pointing in the same direction. what will be the motion of this particle, assuming that initially it's moving with the velocity. It's coming from outside with an initial velocity pointing upward. Exactly, it will move to the right, but also will rotate. That's the helicoid. It will be like this, like this, like this, like this. Graphically, it will do this. Like that. Accelerating in this direction, and this force may work. This is the force which works. Electric field is not lazy. It works. And you have to sum those two forces, then plus Q times magnetic field. And combine it. Let's put the vectorial character plus B cross B. Some people call this, I think, Lorentz force. They call this Lorentz force when they combine the electric and magnetic force together in the same problem. But of course, separated, we have magnetic force and electric force that combined. And still, we have not reached the generation of magnetic field or these kind of things. We will see in a moment. Now let's go. Before putting some slides, I will go to do some intuitive issues. Let's assume you have a wire here. You have a wire. This wire is charged positively, negatively, positively, negatively, positively, negatively. I put a voltage here, 1, difference of voltage 1 larger than voltage 2. Naturally, the current will flow in this direction. Remember, the current flows from high voltage to low voltage. So it means the electrons will flow in the opposite direction. Remember that. Velocity. The electrons move very slow in a direction opposite to the current. Very slow. They collide with many impurities, etc., except in the superconductor conditions, which we explained before. This current generates a magnetic field. Because the motion of charge itself generates a magnetic field. So what's the direction of the magnetic field? Then let's apply the rule. This is a rule you have to learn. This is with the tongue. What do you call this finger? Huh? Tongue, yeah. Not Tom and Jerry. No, it's a tongue, the other tongue. Okay. Then you point with your fingers this direction, and your palms tell you the direction of the magnetic field. So the magnetic field is rotating around the cable. So, and how do you represent this in a 2D surface? Because this is a 2D and it's a 3D problem. Then we put dots. Dots upper means the arrows are going up. These are the heads of the arrows. And the magnetic field enters below. Cross means the tail of the arrow. Then when you see in the textbook, you see that they put some X here. It's not X5. I mean, X means the arrow is entering here and it's going out from the top. Right hand side. So in an exam, for example, if I ask you, tell me, portray the magnetic field here. What do? You put some dots here and some cross here, and I understand that what you're saying is that the magnetic field comes from the top, surrounds the cable, and enter here, and circularly move around the cable. If I stop the current, what happened? The magnetic field stopped existing. The existence of the magnetic field is over. So the magnetic field, the motion of charge generates magnetic field. Now, what happens if I just put one charge, let's say positive charge, moving to the right without any external magnetic field? Forget this magnetic field. This charge, the motion of this charge generates a magnetic field. Because electric current is motion of charges. So if the positive charge moves to the right, it's like a little current, a small current, the quantum of a current, let's say. And then it will have a magnetic field surrounding it. tiny, but it will happen. Well, it depends on the magnitude of the charge also. Now, what happens if I put a charge here to see if you understood this part? Now, this magnetic field is generated by this electricity. I put a charge here, positively charged here. If I put this charge, what is the magnetic force that this test particle feels? It's not moving. Zero. Zero, remember? It's QV cross the K. Now, what happens if this particle, let's assume that it moves down. I put something, I put an electric field here and I made the particle to move, or I put the electric field in the top and I made the particle move down. Or with my hand or whatever, I push it down and start to move with some velocity. Which direction will move this particle effectively? Or where's the direction? What is the force this particle feels? Magnetic force will affect the motion. Of course, the tendency is to move down, but it's feeling a magnetic force because there is a magnetic field. Once you move, you have a velocity inside a magnetic field, you feel a force, you feel the magnetic force. Then what is that force? QV cross B. Let's put that this field, we could calculate B, the magnetic field. Later we will see how to calculate. There is a law called Ampere law, which we will see is equivalent analog to the Gauss law, and it will allow us to calculate magnetic fields surrounding cables and certain geometries. So the force, the magnetic force, of course, is Q, the test particle, its velocity, cross magnetic field. Right-hand side rule again. QB, the magnetic field is entering here. So this particle will have the tendency to feel a magnetic force in this direction. And then effectively will move like this. This is the principle of the cyclotron. You remember those, when they put these rings and they put charges to move circularly? Well, it's more or less, this is the idea. That's the idea. Now, we understand the magnetic force. We understand the direction. We know that it doesn't have any work. We understand the Lorentz force, which is the combination of the electric and magnetic force. We understand how to generate magnetic fields from currents. Still, we have not seen how other induction lab. We will isolate ourselves in magnetism now. Let's study the Ampere law and Biot-Savart law. In Biot-Savart, we can do calculations, but I don't want to spend time because you are in general physics. We could do calculations in Biot-Savart, but those calculations are tedious, tiring. It requires some skills in integration, which we could do it, but I think it requires some several sessions of training. But we will see superficially. And the Ampere law is one which we can certainly see because it's very simple in this class. At the level of this class, what you care is that there is a magnetic phenomenon, more or less how it works, and so on. So let's go. I will switch on the projection here. And then I put Ampere. So I will simply have that. Oh yeah. So concentrated. Bonus. Super Mario. Okay, look at this. It's a oops, I was catch. No, it's okay. So the Ampere law in a rigorous sense is expressed in this way. Is it rotational? This object is called rotational. You will not learn in this way because it's complicated for you. And this is the derivative instead of displacement, but we will not see in this way. Displacement is basically electric field. It means changing electric fields in time can generate magnetic fields, and this is a current. And the current also can generate. So the Ampere law is telling me that the closed integration is a line integral is equal to or is proportional to the closed current. And this is an example. Examples, we will not use H, we will use B because we will work the simple cases. Then in our case is the integral of close of the magnetic field times the line which it surrounds is equal to mu sub 0 times the closed current. Mu sub 0 is another constant which is measured, and we will learn the nature of that constant later. But what is this line of integration? Let's assume this electricity, this current is flowing in this direction. So naturally, the magnetic field will surround the cable. No? It will be like this. The magnetic field direction. If we look this frontally, frontal view, I put myself here, what I see is this. The current moving in this direction and the magnetic field doing this. The magnetic field is rotating around the cable. Then I can imagine, I can paint an imaginary line. Cylindrical. It's just a circle. Then I can execute this integration easily because it will be the magnetic field times the line. The line is a circle, 2 pi r. R is the radial distance between the center and the circle. Is equal mu sub 0 current close. And then at the end, the magnetic field is divided 2 by r. So it means that the magnetic field is proportional to inverse of the radius. The farther I move from the cable, the smaller will be the magnetic field, and I could find it easily by using the Ampere's law. These calculations I will ask in the test because it's very easy to do. It's not like the Biot-Savart law. The Biot-Savart law, I know how to do it. I studied that in university, but I had the feelings that there is not enough time. It depends on your skills. We can try. Well, I don't know how good you are in this part calculating right now by using integrals, and especially because these integrals involves cross products. And so it requires some special skills, but there are some types of problems which can be done. We can take a look at it anyway. And yeah, this is the picture I was saying. The electric field. They represent this H, like current 2 pi r, but because they use H instead of B. This is not exactly the magnetic field. Actually, this is the magnetic field divided by mu 0. Okay? Because sometimes they represent this H instead of B. We will see later what is the meaning of this H subsequently. Now, let's go to the Biot-Savart law for finishing this session. And next session, we will go to electromagnetic waves, and we will do problems. We will solve problems. The Biot-Savart law is more or less a little bit the same. You have a current flowing, and you have a magnetic field. And then there is a law. This is the equation. It looks really, really small here, ridiculously small. But look at the essence. Let's review the concepts. Look. The direction of the magnetic field. The electricity flows in this direction, the current, and the magnetic field rotates around this cable. Now we see the calculations of the Biot-Savart law. We will evaluate that in the next class, but the expression for the Biot-Savart law is this. I will zoom it here. Is the differential of the magnetic field is equal to mu sub 0 divided by the current multiplied by the element cross product, the vector current cross product, the element of line of the cable divided R squared. And then, of course, the idea is that you have to integrate this. This cross product at the end finish being current, yes, sine of theta, which is the angle between the element of line and the direction of the current. So, well, I mean, as I say, there are some samples. I will try to find simple examples for applying the Biot-Savart law for you to understand how does it work. But in the test, I will not ask difficult problems about Biot-Savart, because what I care from you right now is that you understand this issue. Now, well, we could cover this part. Now let's go to how to generate a variational magnetic field. Changes in the magnetic field can generate electricity. And that's the principle of the generator. In other words, let's put it in this way. If I have, before showing any slides, let's assume I have a cable here. For that part, I will switch on. I will switch on here. I will switch off here. After this cable, this wire is not, there's no electricity flowing, anything, nothing. Let's assume I put a magnet here with a north and south pole here. Naturally, the lines of the magnetic field lines will do this. But some lines will be able to cross here now, the wire. If I approach this magnet to this wire, I will induce a current. A current will start to flow here. What is the direction of that current? Do you have any clue? Is this way or the other way? The tendency, I will give you some clues. The tendency of any system in nature is to keep the initial condition. This guy, when I approach this magnet to this wire, the wire is feeling that the magnetic field lines are increasing. The wire doesn't like this. The wire wants to decrease those lines. So it tries to generate a current such that it contrasts. It creates the opposite, a magnetic field in the opposite direction if I approach. So in which direction do you think the current is generated? I move this to the right. Let's put a velocity here to the right, and then the lines are increasing. This guy will try to generate lines in the opposite direction. Magnetic field lines in the opposite direction. If it goes here or it goes here.
Like this, towards us.
It should be here, no? Should be in this direction, so it means let's put the arrow here. The current induced, there is an induced current in this direction. And try to contrast. The opposite happens if I put this object and I put far away, the magnetic field lines are decreasing. The material, the instinct of the material is the tendency to keep the initial condition. Then it tries to increase the lines. So the current will flow in the opposite direction in such a case. Guess what? This is how the electricity comes to our houses. How is that? Let's explain that a little bit. Let's assume that you have an hydroelectric or carbon or nuclear plant or whatever. Let's do the hydroelectric case, which is the simplest. the hydroelectric principle is you have a fall of water. Water falling, water is falling. You have a turbine here. Turbine. When the water falls, this turbine rotates. What is inside this turbine? Let's may assume inside it has something like this. A wire, and this is connected to the paddles. So this rotates, and there are some magnets. There are some magnetic field lines entering. We put those magnets inside. We put it by purpose, but this is rotating. When it's rotating, what happens? There is a change in the flow of the magnetic field through the wire, because sometimes the plane of the wire is facing directly the magnetic field. But there are moments when you rotate this 90 degrees, there is no flow of line. There is no line flowing through the area. And when it rotates 180, is the opposite, it changes direction. That's why the current we generate is alternate current. It's AC. It goes one direction, comes back to the other direction, then goes with some frequency. The frequency depends on the frequency rotation. This is how the electricity is generated in the houses. And then you go, then what these guys do, I will advance a little in time because there is no time now. Well, in the next class, we will see this. Well, you generate the electricity here. These guys send this electricity to some transformers. Transformers are objects like this. Objects like this, and they have some wires. We have some cables here. And depending on the relation, the number of turnings, it will be amplify or decrease the voltage. Okay, so when this electricity enters this part, it will create a magnetic field which flow through this material, and it will go to this. Since it's alternate, it oscillates. And that oscillation will induce an electricity in the other side. And this, you increase the voltage, high voltage. Why do you want to increase the voltage for sending the electricity to the houses? Because you want to minimize the losses. You want to save money. And remember that the power of transmission is the current times the voltage. For a given power, if you increase the voltage, you decrease the current. When you decrease the current, you decrease the losses, because the power loss is proportional to I squared R. So you reduce the current, or the amperage, as people say technically, you reduce the losses. Then when the electricity is going to arrive to the house, what happened? You use another transformer which does the opposite. It reduces the voltage and increase the amperage, increase the current. And then you will say, well, you lost. Yes, because that's the idea. In the house, you have to lose that energy has to be lost. And that's why the companies charge you money. Then why nuclear energy is cheaper than hydroelectric energy? Because it's more abundant. Now there is another way to generate electricity is using thermal plants, where you put some carbon plants, you put the heat and you expand a gas, and the gas move the turbine. The same. But the idea is, as far as you can move this thing, you can generate electricity. That's it. This is how the electricity is generated in the houses. It's one of the most useful applications in physics, no? We can have electricity thanks to that. But electromagnetism is not reduced only to these engineering applications. In biological systems, etc., it's applicable in fishes, whatever. I mean, you will find that it appears everywhere. But coming back to this point, that's why people are trying to find superconductors at high temperature. If we have superconductors at high temperature, what will happen? We don't have losses in the cable. Even if you minimize the losses by doing this, still you lose something. what the companies they charge to you is the work it takes to transmit the electricity from the source to your house. That's what they charge you. That's what you have to pay. And why in high developed countries, which has nuclear plants, the electricity is so cheap? Because they have a lot. When the electricity in my country, we have in the 90s, in Colombia, we have, there was a moment was very hot and the rivers decreased the level. There was no water. They had to cut the electricity every day during the afternoon because there was not enough water for doing this process. We don't have nuclear plants there. And we didn't have these thermoelectrics. That's the proper name. The thermoelectrics were not properly developed. There was no backup plan for the country. They had to cut the electricity. Imagine living every day from 2 p.m. to 8 p.m. without electricity for 1 year. It's a disaster, no? Imagine. It was a complete disaster by then. The production decreased. Many food get decomposed if you have to planify many things in advance. Of course, the electricity is cut during daytime. Even the time, the schedule was changed. They put they shift the hour one, or they shift the time by 1 hour by then, etc. Well, take into account this. We will see this next class. Why? Because in the exam, I will ask questions about these transformers, amperage, voltage, blah, 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 and so on. And with this, we close. I think what is missed, displacement current is the only thing which we have not seen, because without the displacement current, we cannot symmetrize the Maxwell equations and we cannot have electromagnetic waves. So next class will be electromagnetic waves, displacement current. We will close this chapter and then we will do or solve certain problems. So for today, that's all. Thanks for coming and see you next week then. Then let's close here.